So welcome again, Joris van Slageren from Stuttgart University. And he will talk about terahertz EPR in molecular nanomagnetism.
Thank you very much, Monica. So yeah, well, it's a third talk about terahertz EPR. So of course, the risk is that we are getting some overkill in this area. But I believe that this short presentation is going to be somehow complementary to the previous two speakers, so Alexander and Sergey. And this is essentially because we are from different areas. So Alexander likes to study materials that have some biological relevance. Sergey, of course, is a solid-state physicist. And we come from molecular nanomagnetism. So I just wanted to show you a little bit about molecular nanomagnets, what the aims of the field are, and some of our contributions, of course, to this area. So traditionally speaking, a molecular nanomagnet is a transition metal complex, or usually these are complexes of more than one transition metals. And then since a decade or so, these are also 4F elements, so lanthanides are involved with, which I will not speak about today because of time reasons. So that means that these are very somehow similar to magnetic nanoparticles, but they are absolutely monodisperse. And that means that even though we will study powder samples or single crystals, because the ligand shell around these metal ions is shielding the magnetic core from the surroundings, these molecules are isolated, and we are going to be looking at the molecular properties. Now, one of the things is that, of course, the magnetic ions here in orange and in green interact through super exchange interactions. And this usually leads to a rather well-defined spin ground state, which can usually be looked at in terms of spin up, spin down pictures. And this can lead to spin ground states that have very, very large spins. And the second ingredient that is important is that there is an anisotropy of the magnetic properties. There is an energy barrier between up and down orientations of the magnetic moment, which are the ms plus s and the ms minus s states of the spin ground states. Now, the point is, of course, this would be true for a magnetic nanoparticle. And of course, you can imagine that if the thermal energy is small compared to the energy barrier, if I prepare the system in a 0 state or in a 1 state, this magnetization, this magnetic moment is stable over time. And this is where the idea of information storage using these sorts of system comes from. Now, what we need to realize, of course, that in molecules, the spin is large, but not infinite. So that means that there is a quantization of the orientation of the magnetic moment of the spin, which is characterized by, of course, the magnetic spin quantum number ms. And that means that instead of having just a simple double L potential, we have a number of allowed spin orientation as given here. Now, in the simplest case, the energies go proportional to the ms quantum number squared, where there is a proportionality constant, which is the second order or second rank axial zero field splitting constant. And that means to a first approximation, the energy barrier is given by this anisotropy constant, the zero field splitting constant d times the square of the total spin of the ground states. Good. Why are people interested in this? I alluded to this already, of course, and the idea is data storage. So a standard magnetic hard drive would look something like this. These particles are maybe 5 to 10 nanometers, and I need about 100 of them to define 1 bit of information. And how do you go from there? How do you increase the data density? First of all, you can, of course, then try to organize these particles in so-called bit pattern media. But what you see is that the length scale here is not changing. So you can maybe gain an order of magnitude, but not more. Of course, on the other hand, molecules, because they are much smaller, they are about 1 nanometer in size, and you can organize them on surfaces in regular arrays. So the idea would be to store bits of information in single molecules, and they are single molecule magnets. Now, of course, I'm not talking about your hard drive in your computer because it doesn't exist anymore and has been replaced by a solid state drive. But to give you some idea of where large data quantities are needed, at some years ago, we had the picture of the black hole. And this orange donut thing is actually the result of 1 petabyte of data. So there is a need for storage of large amount of data. But of course, we are here talking about EPR, which therefore we should figure out why EPR can play a role in here. And the reason is essentially because the transitions between these spin orientations are all, of course, EPR transitions. The MS quantum number changes by plus or minus 1. So these transitions are excited by the magnetic field component of electromagnetic radiation. Now, for your benefit, I have changed the energy scale to terahertz compared to the, for me as a spectroscopist, more usual reciprocal centimeters. And you can see that these transitions are in the hundreds of gigahertz. And that, of course, leads us automatically to high field EPR. And the typical way, of course, in how the field progressed is to make a molecule, to look at the magnetic properties, determine the energy barrier, and then do many EPR measurements at very many different frequencies to try and reconstruct this energy level diagram. And then, of course, to see how this relates to the molecular structure with the aim to improve these molecules. Now, this is rather inefficient. You are looking at some splitting in zero field, and you do this by recording measurements as a functional field at many different frequencies. Wouldn't it be much better to do this in another way? And of course, this is what we try to popularize for a long time already. And the idea is that EPR is normally done at some fixed microwave frequencies, increasing the magnetic field until the resonance condition is fulfilled. But of course, what we could also do is change the frequency, and then of course, radiation is absorbed as the resonance condition is fulfilled. For that, of course, we need frequency tunable sources, which in the terahertz are available. At the time, these were these backward wave oscillators already introduced by Sergei, which allowed us to do this. And that means we could take one of these single molecule magnets. This is a manganese 6, spin equals 12, ground state. And we can scan the frequency here from 4 to 10 reciprocal centimeters. And by this single 30-second scan, we have already characterized 6 transitions in this system. So it is a fast technique from that point of view compared to the 15 minutes or so that you would require in the field domain. But of course, now that we have somehow decoupled field and frequency, we can also look at more interesting things. So one of the things we can do, of course, is then rather than have a single pass transmission spectrometer, we can incorporate an interferometer, and by that also look at the frequency dependence of the phase shift due to the magnetic resonance. And from these two sets of data, the transmission and the phase, we can reconstruct the magnetic permeability and its frequency dependence without any sort of model. And this, of course, can be interesting, especially to characterize ordered magnetic materials. This is done on manganese 12. And of course, then what we could also do is to look a little bit more at circular polarized radiation, as Alexander also showed. You can excite either the delta MS +1 or the delta MS -1 transition selectively. And what we could also show in these single crystal mosaics is that actually the plane of polarization of the linear polarized light is rotated by quite a bit. So not only is the one circular component absorbed more than the other, there is also a Faraday effect, and these Faraday effects can be huge, up to 100, more than 100 degrees for a 0.5 millimeter thick sample. Of course, it is this effect that is used in the ferrites, which are part of the quasi-optical systems that many people use and that were introduced by Richard Wilde. Now, again, because we have decoupled field and frequency, by having these frequency swept sources, we can also look at some other things. For example, at the time dependence, and look at the magnetic relaxation of these manganese 12 single molecule magnets. The zero field transition would be here at 10. And then if I cool down in field, then the system will be magnetized. And of course, the resonance frequency would be slightly higher because of the Zeeman splitting, but it would be more or less here. But what I can do is then quickly invert the field within the relaxation time. And of course, at that point, I have to subtract the Zeeman interaction from the zero field transition, and I end up at slightly lower frequencies. I'm more or less at this point in the double well potential picture. So most of the molecules are here in this metastable state. And I can just follow the spectrum as a function of time. And of course, from that, arrive at some effective relaxation time. So that is something that we did. And then when I moved here about a decade ago, we said, well, it's nice to do this in the frequency domain, but why not use both possibilities, so to sweep the field and the frequency. And this is the spectrometer that we built up here. It looks kind of familiar. So this is the quasi-optical bridge by Thomas Keating. And I just, because it has the name, the word has been used a couple of times already, just to show you a little bit how this measurement works. So the radiation that comes out of this source is linearly polarized, which of course I can see as the sum of two circular polarizations. Now, this is then going to the sample, nice animation made by Bertrand Neugebauer. And then of course, when it arrives at the sample, as we have seen, the two circular components interact to different extents with the sample. And that means that, first of all, the radiation is no longer linearly polarized, but elliptically polarized, but we have also seen the Faraday effect, so the planar polarization is also changing. And that means that I can now detect the component which is perpendicular to the original radiation. So of course, if there is no interaction, the radiation will be still linear, and this perpendicular component, it would be zero. If there is some magnetic resonance, then there should be a signal. So this is a way to detect EPR on a zero background. As I've said before, EPR is an inherently insensitive technique. Of course, we did not come up with this, and Richard has talked about this before. I can also detect the copolar. So it's Petra who built up this spectrometry, is now back in Brno. Good, so this is what it looks like. We by having a set of VDI sources, we can go up to 1 terahertz more or less. And one of the things that we can do is now, for example, measure in the frequency domain while slowly sweeping the magnetic field, and we end up in these sort of 2D field frequency maps, which is not individual points, but just about 10,000 spectra or so. And this takes a number of hours, but in the field domain, this would take many, many months. So this is just an S=4 ground state single molecule magnet by Philip Lutz here, then from my group. We can also look at, of course, solid state materials like these ferrites, where you have the ferromagnetic, quasi-ferromagnetic, quasi-antiferromagnetic resonance mode. And then we found out that there is an additional feature here, which had not been reported, but then of course, about 2 months after we did this measurement, somebody reported this. So anyway, this was just to see if we could find a proof of principle sample for the Peter project. So it was not something that we were interested in pursuing in great detail. Now, why are there no manganese 12 in my hard disk? And the reason is that if I make a larger molecule, then the anisotropy is going down, because it essentially is a linear combination of the anisotropies of the single ions. And these coefficients are decreasing if I make the molecule larger. So the only thing that the tuning knob that I have left is to look at this single ion anisotropy. And this is, of course, what the field decided maybe 10 years ago, is to do that. And one ion that exists that has a much larger anisotropy is Cobalt 2, which has a 3 ampere spin, so S=3 halves, and MS plus minus 3 halves and plus minus 1 half are separated in spin Hamiltonian picture by 2D. And this is, of course, an EPR transition, so I can start to measure this. We did this in a series of cobalt complexes made by Ivan Nemec, then in Olomouc. And we determined all the Ds and Es. And of course, one of the things that is interesting in molecular nanomagnetism is to try to relate this to the structure, to some bond lengths, bond angles. And then rather than try all of them, Rafa, the PhD student involved, just tried all of them automatically. Now you would probably call that machine learning. At the time, we were just doing this analysis, and he found 2 very interesting correlations with D, which is very strongly correlated with these 2 angles, so an elongation of the tetrahedron, and E, which also, and this is, I guess, still the only correlation of E that is somehow robust, which is a strange measure, is the product of these 2 parameters. And you can see that these are the many correlations that he tried, and certainly in D, this correlation is much better than all the other ones. This is the error. Now, these D values, I just briefly skimmed over them, are 10 or so. This is not so dramatic. So let's see if we can increase this. And this is then this cobalt complex. And because this angle is very acute, and because the ligand has 2 negative charges, this leads then to an enormous zero field splitting, which we published some years ago. And already from the magnetic measurement, you can see that there is a decrease of magnetic moment, which we can attribute to the zero field splitting. And at this point, the fitted energy gap is about room temperature, I would say. So 230 wave numbers in EPR terms, this would be 7.5 terahertz. There is not even backward wave oscillators or molecular gas lasers and so on arrive at these sorts of frequencies. So the only possibility that is left is to do infrared spectroscopy. So we coupled the infrared spectrometer with our magnets. Actually, these measurements were done somewhere else, but these things we can now do ourselves as well. I apologize for the poor quality of an interferometer picture. And this is then what we see. So these are the transmission spectra as a function of wave number. And you see that there are many, many phonons. And only in this middle part, the response, the transmission spectrum is dependent on the applied field from 0 to 11 Tesla. If you zoom in here, you see this picture is actually quite complicated. You can divide all the spectra by the spectrum at 0 Tesla, and you see that for these sorts of systems, the response is actually quite strong. And we attribute this to spin vibrational coupling. This is currently very popular in the field to look at these things in more detail. We did not pursue this at this time. And that means because we have now strongly fixed this energy gap, we can now look a little bit more at the relaxation mechanisms, because traditionally people would only have some sort of general relaxation constant over the barrier here, and not worry too much about what the nature of the mechanism of the individual steps here, which will be the spin lattice relaxation process in EPR terms. And essentially there are three possibilities. You can directly go from one state to the other. You can go in a two-phonon process by a real intermediate state. So this would be this transition here, or you can go via a virtual intermediate state, which is then called a Raman process. And then by fitting the relaxation time, here's a logarithm over the inverse temperature, we could actually figure out that in these systems, because the energy barrier is so high, we have essentially excluded this from the relaxation, at least at low temperatures, and most of the relaxation proceeds via this virtual intermediate state. Good. I did not want to talk about the lanthanides. I just wanted to give you a little overview over the various topics in molecular magnetism where we can use terahertz EPR. I tried to show all the pictures of the people involved during the talk, so I thank them very much. Of course, me as the group leader, I only do the PowerPoints. At least I'm good at something. I leave you with the funding slide. These are the people. Of course, at this point, I have to especially thank the EU and the Peter project for funding a large part of the activities in my group during the last year. So with that, I would like to stop, and I thank you very much for your attention. And I'm happy to take any questions. Thank you very much.
Okay, thank you, Joris, for the nice talk. So time for questions. Any question?
Maybe I will.
Okay, yeah, go ahead.
So very nice presentation, Joris. Which BW do you have? It's OV86, I believe, shown on the picture.
So what we have, and so the results I showed were from the time that I was in physics here, and you know that Martin Tressa has a essentially full set of BWOs. At the moment, what we have is what we call the QS2. Oh God, I used to know the conversion.
Okay.
That is, and we have the what is that, QS 1000 or so, 1500 with some broadband doublers by VDI.
So you're using OV86 plus doublers and triplers.
Yeah.
Okay, thank you.
Well, of course, at the time we were using the high frequency BWOs, but since these then at some point became more and more difficult to obtain, we switched to this alternative solution of having doublers and triplers.
But from your point of view, for instance, so you tried several techniques, right? So you tried frequency domain spectroscopy, you tried fine infrared spectroscopy, you tried just normal ESR classically. So my concern, of course, I mean, high field ESI, it's perfect techniques, but it takes so much time compared to what you can do with, for instance, Fourier spectroscopy. Mm-hmm. Incredibly high, or for instance, frequency domain spectroscopy. Would you think the future, say, where it goes? I mean, in the future, what would be? I mean, we have another opportunity. We have also time domain spectroscopy, right? So with this antenna-like terahertz spectroscopy.
So I try to compare all these techniques in some review I wrote some years ago. Mm-hmm. I think for a standard, if I just want to determine D, let's say, I can do a standard terahertz or high frequency EPR measurement, and then I use three frequencies, and this is usually enough. So in terms of much of the production work that we do, this is what we do. Of course, I can measure much faster in the frequency domain, but if I use single frequency domain measurements, then of course I showed you the nice examples. The problem is always going to be the standing waves in the system. And we have come to great extents to fight these with implementing 2 quasi-optical isolators, and really this really improves the situation by a lot. But then if I do 3 field domain measurements, this takes me, I don't know, 45 minutes or so. I can sweep up, speed down, speed up again, and then I'm essentially done, right? But of course, if I need to look at these systems more in detail, make field frequency maps, then being able to do this in the frequency domain is an enormous advantage, because I can always then, after I have this map, I can make cuts along the field axis to avoid the standing wave problem. And so that means that I have both the advantage of being able to measure fast, because I measure in the frequency domain, and of course I can do this in many different fields at the same time. Now, comparing this to the time domain measurements, this has improved enormously, I would say. At the time when I thought about these things, the intensities were very low, so that means that if the sample was not transparent enough, this was an issue. And of course, the resolution at that point depends on the delay stage, how far I can shift the delay stage. That means that I need to do some proper aligning of the whole setup in order to get these measurements. Now, Alexander mentioned this before. Professor Nelson has shown recently some very, very interesting results. And potentially this can also lead to pulse measurements and so on and so forth. So there is an enormous potential there. It depends again. If the nice thing, just like I did not talk about the infrared. The infrared, of course, is nice. It does not work much below 10 wave numbers, I would say. So if you have something where you need to see something at 100 gigahertz, 150 gigahertz, you can easily go there with EPR. With infrared, it's more difficult. The nice thing about the infrared is, of course, that you get the whole frequency range. Resolution is usually okay. But it's the lower frequencies where then the sweepable sources, whether these are BWOs or the multipliers, still have a big advantage, I would say.